If you can read the time on this clock, you might be a nerd too. Welcome to part 2 of building a binary clock. In this video, we'll do a quick overview of binary, what it is and how to read it. We'll talk about the packed BCD format we're using to display the digits on the clock. We'll look at all of the electronics used, how they fit together, and the circuitry. We'll look at the computer code running on our microprocessor, which serves as our traffic cop controlling all aspects of the clock. We'll get it all assembled, soldered, and fit into our case, where we'll get it tested and we'll talk about how the clock operates. I'm really excited for this video because it combines my interest in woodworking with my passion for electronics hobby projects. So come along as we get this all put together and build a clock that very few people can read. And in the words of my wife, why would you want to tell time like that? Before we get into the clock itself, let's take a quick detour and talk about binary. I'm sure most of you watching already know this, but I want to cover it quickly and give a refresher. And if you're new to this, don't worry, I'm keeping it simple. Binary is just another way to count. We're used to decimal or base 10, which uses 10 symbols 0 through 9. When you run out of symbols, you roll over to the next place value. So we start at 0, 1, 2, all the way to 9, then 10, 11, 12, and so on. Binary works the same way, but instead of 10 symbols, it only has 2, 0 and 1. When you run out of symbols, you roll over to the next place, just like decimal. The place values are 1, 2, 4, 8, 16, and so on, and you start from the right and read the number out to the left. So when you see 1011 in binary, that's 8 plus 0 plus 2 plus 1, which equals 11 in decimal. Same number, just a different number system. Now for this clock, we're not using pure binary, we're using BCD or binary coded decimal. Instead of one big binary number for the whole time, each place value on the clock gets its own set of LEDs. Reading is easy once you get the hang of it. Start with the tens column, add up all the LEDs that are lit using their binary values, do the same for the ones column, put them together, and you've got your digit. In the example, we've got 15 hours, 37 minutes, 6 seconds. Put them together, 15:37:06 or 3:37 p.m. Do that for hours, minutes, and seconds, and you're reading a binary coded decimal clock like a pro. Here are all of the parts that we're going to need to put this circuit together. We need our Arduino. This is an Arduino Nano. We need our real-time clock module. We need 3 of these little 74 HC595N shift registers. We need some resistors. These are 470 ohm resistors, and I chose those because with the LEDs I'm using, I wanted to make sure I didn't exceed the max per pin draw, power draw, or the max per chip power draw of these little shift registers. They're not really designed to push a lot of power through them. We need a potentiometer to control the brightness, an electrolytic capacitor that goes across the 5-volt rail and the ground, a couple of momentary push buttons. These set the hours and minutes. Obviously we need our LEDs. They're 10 millimeter LEDs, which are twice the size of your standard 5 millimeter panel mount LED. So even though they're only twice as big, they visually pack a much bigger punch. They're very impressive in person at how much larger than a normal LED these are. I also have these little plastic panel holders for the LEDs, and these were chrome plastic, but I didn't like the chrome with the black buttons, so I just painted those black. We also are going to need either our circuit board or a hobby board to wire everything up on. And I created a little panel that our printed circuit board can mount on, and this will get affixed to the back of the clock base, and then the circuit board mounts here on standoffs and screws down, and that'll hold everything together. So this is all we need to assemble the circuit and get the clock up and running. I want to talk quickly about the cost of all of the electronics used in this project. I don't have the bill of materials in front of me, so I'm going to stand here awkwardly while VoiceOver Me outlines everything over here to the side. I got a 3-pack of Arduino Nanos for $13.99 or $4.66 for this project. I got 25 shift registers for $6.99, 28 cents each, or 84 cents for this project. I got 5 real-time clock modules for $9.99 or $1.99 for this project. I got 110 millimeter LEDs for $14.99 or 14.9 cents a piece, $2.99 for this project. I got 25 LED panel mounts for $8.99, 36 cents a piece, or $7.19 for this project. I got 10 dip sockets for $6.95 or 69 cents a piece, nice, $2.10 for this project. You can get a couple hundred electrolytic capacitors for about $10 or roughly 4 cents a piece.
so 4 cents for this project. I got 100 470 ohm resistors for $5.99, 6 cents a piece, or $1.20 for this project. I got 5 push buttons for $8.99, $1.80 each, or $3.60 for this project. You can get 32 prototype boards for about $7 or 22 cents a piece. And I had PC boards manufactured. I paid $71.27 for 10 or $7.12 a piece for this project. I bought a 17/32 drill bit for $10.93, and now I have an oddball drill bit for my collection. So the total for electronics, not counting wood or 3D parts, was $42.66. Okay, awkward me, back to you. Thanks, VoiceOver Me. And if you'd like to build your own binary clock, I have links to everything down below. Looking at the circuit, it's really not as complicated as this wiring would have you believe. At a high level, we've got an Arduino, we've got our shift registers kind of hidden down inside of these wires. We have the real-time clock module, we have a potentiometer, a couple of buttons for setting the hours and minutes, a capacitor that just helps decouple and smooth any transients on power. And then we have our LEDs. And on this breadboard, they're actually oriented 90 degrees from how they are in real life. We have our hours, our minutes, and our seconds. The real star of the show is this inexpensive real-time clock module. It uses a CR2032 battery to keep the time. And all the Arduino is doing is asking this for the time. If the time is set, the Arduino reads it out and pushes it out to the display. This has not been plugged into any power source for 4 or 5 days as I've been working on the video. So if I turn on my battery bank, we'll see the display come to life, and we will see that it is displaying 17 hours, so 5 o'clock, 5 p.m., and 47 minutes. Have to do a little bit of thinking and counting. And then the seconds are ticking up. So we have our tens place represented here. We have our ones place represented here in this circuit. And so again, being packed BCD binary, we've got our positions as 1, 2, 4, 8. So we add them up. 1 plus 2 plus 4 is 7. So that is 7. 1 over here in the tens place is 10. So 10 and 7, 17. And then likewise over here for the minutes, we've got 1, 2, 4. So 4, 1, 2, 4, 8, 48. So 5, 48, and the seconds are counting. Anyway, it came right back to life as soon as I put power in it because the battery in that real-time clock module is keeping the time and keeping it stored. I realized that this looks a little bit more like a bomb than a clock, but it really is a clock. And we'll get down deeper into the circuitry and take a closer look at each individual component and how it's wired up. Moving some of our jumper cables out of the way, we can see that the Arduino doesn't really have that many connections that we're using. We need 3 pins, which are these 3 right here, 12, 11, and 8, which are pushing the data to the shift registers. We've got this pin, which I believe is 6, which is doing our pulse width modulation for the brightness. That is reading in from our potentiometer over here, one of these analog pins. So as we adjust the potentiometer, it is changing the PWM value and sending it out on this pin. We have our 2 buttons connected to pins 3 and 4, so that when we push the buttons, we can increment the hour or the minute. The real-time clock is wired to 2 pins, and these are the I2C pins that does all of the communication with the real-time clock. And then it's actually being powered off of this 3.3 volt rail. I was reading that the real-time clock module is happiest at 3.3 volts. It will run at 5, but when you're running it at 5, it can cause problems with the battery, and it seems to be perfectly happy on this 3.3 volt rail. Moving over to the shift register, these are just generic versions of the Texas Instruments 74HC595N shift register. I got these off the internet. They're very, very inexpensive, discrete CMOS logic, and all they do is take clock pulses in from the Arduino, and they are all tied together here, and they shift bits out, which are all of these wires here that go to the resistors and then to the LEDs. Here we have a 10K ohm potentiometer, and all that's doing is giving us a variable resistive load that the Arduino interprets into brightness, and it just maps it from LEDs all the way off to LEDs full brightness. And this is our DS3231 real-time clock module. It's in a vertical orientation, so it's a little hard to see, but there are circuits and ICs that are on the board. And then this black piece is the CR2032 battery holder. These are the momentary push buttons that increment the hours and the minutes. Every time you push them, hours increments by 1 from 0 through 23. Every time you push the minutes button, minutes increments from 0 to 59. And it just rolls the displays over. Here we have our LEDs, which represent our binary digits, and they're rotated 90 degrees. So they still work the same way, but you have to look sideways at this breadboard. Each LED is tied on the negative side back to the shift register and through a resistor to the positive side, so we are syncing current. You can also see that these LEDs are flickering on the camera, which you absolutely can't see in person, and that's the pulse width modulation that comes from the duty cycle. So as we brighten or dim the LEDs, it's actually turning them off and turning them on very, very rapidly, and that gives a flickering effect on the camera, but to our eyes, it comes across as brighter or less bright. I had originally intended to use one of these little project perf boards to solder all of the components and build my circuit. This is a 70 by 90 centimeter project board, and I needed this size to really hold all of the components comfortably, be able to solder everything together and make it fit. But it's a bit of an odd size to put onto the back of the clock base and have everything work the way I wanted it to work. I did solder one project board with all of the components, and I got it all wired up and connected together. It turned out looking like something that you wouldn't want to take onto an airplane or show to people in an American school. And at 70 by 90 centimeters, it's a little bigger than I wanted. Coming up with a case that would hold this and fit on the back of the clock and still be nice and tidy was going to be a challenge. So I went the route of having a custom PCB made. I spent an afternoon learning KiCAD, an open source suite that lets you build schematics, design PCBs, and create the files necessary to send off to the companies overseas that will manufacture custom PCBs. $71 later, I had 10 PCBs in my hand, and I was able to put it together and solder everything on, much less messy, a lot nicer and neater. I used an open source tool called KiCAD to lay out the schematic and design the PCB. I have never used a schematic layout or PCB editing tool suite before, and so I spent about a half a day getting comfortable with the tool, learning how it worked, and ultimately building this. So even if you've never used this tool before, within an afternoon, maybe a full day, you can absolutely achieve a similar result. This is the schematic for our circuit, and we're using an Arduino Nano. This is controlling all of the inputs and outputs through various pins. Some helper components are the capacitor, which goes between the 5-volt line and ground. We've got our hours button and our minutes button, and both of those are pulled to ground. We have our potentiometer, which controls the brightness of the circuit. And then down here we have our real-time clock module. Now I tried to build this without using a real-time clock module, but I found that the accuracy of the Arduino's internal clock just wasn't high enough, and I got way too much drift on just having the Arduino clock the circuit. So I found these inexpensive DS3231 real-time clock modules, and I added one in. It only needed 4 connections, so it wasn't that difficult. Then over to the right here, we have our shift registers. We have one for seconds, we have one for minutes, and we have one for hours. All of the shift registers are connected to each other, and then the clock pins are tied back to the Arduino. So every time the Arduino clocks, it drives the shift registers. The shift register's output pins go to 470 ohm resistors, and then those resistors connect to LEDs, which go to VCC or 5 volts. This is called syncing current, and the reason I did that is these little 74 HC595 shift registers can't really drive very much power at all. I believe the specs are less than 6 milliamps per pin and 35 milliamps for the entire chip. So I had to balance the resistor value with the LED forward voltage to make sure that I wasn't drawing too much power at any one time. There are 7 LEDs per chip, except for the chip that drives the hours, and there's only 6 there because we don't need to go as high in the tens place. And that's really the entire circuit. Once you lay out the schematic in KiCAD, you can push it over to the PCB editor where you actually lay out your PC board so that you can generate the files needed to send off and have PCBs manufactured. Once you create your schematic in the KiCAD schematic editor and link all of the pins together, you import those into the PCB editor. And then using the pin mappings, it knows which pins need to connect to which other pins, and you can lay out your circuit board. So here we have our circuit board laid out with all of the components dropped on. We have our Arduino, we have our shift registers, we have our capacitor, our switches, we have our potentiometer, we have the header that we're going to ultimately drop our real-time clock module in, and then we have all of our resistors and the landing pads for the LEDs. By default in the KiCAD PCB editor, you get a 2-layer circuit board. So you have a front layer where you can place traces, and you have a back layer where you can place traces. You can certainly do more than 2 layers, but having PCBs made with 4 layers or more gets pretty expensive pretty quick. So I went ahead and stuck with 2 layers. Probably one of the bigger challenges was figuring out how to do all of the routing of all of the traces on the front and the back. The reason being, unlike with using wires where you can jump over a connection, you can't cross a trace. So it took me a fair bit of time to figure out how to route everything and not cross my path. So I used every bit of the front traces and the back traces to make that happen. There's probably a trick or a way to work around that I just don't know, but I was ultimately able to get it done. Then we can see a rendering of what our circuit board is going to look like. For generating the files that we need, frequently called Gerbers, although there are different formats, to upload and send off to have printed circuit boards produced for us, which is what I did for this project. I'm going to go over the code that powers the Arduino. It's written in C, and it's not very big. It's only 252 lines long, and that includes all of the comments, including this block at the top that explains what the code does and links to our Creative Commons license. At the top of the code, we link out to some standard libraries, the Arduino header library, the I2C wire library, and the real-time clock library. And then we do some definitions at the top, defining the pins that we're using for our shift registers, for our real-time clock module, and for our potentiometer for the brightness. We also define the pins we're using for our buttons and set some variables that help us keep track of things later in the program. If you're not familiar with Arduinos, all Arduino programs, also called sketches, consist of 2 main parts that are required: your setup and your loop. The setup runs one time when the processor powers on, and what we're doing in our setup is we're enabling serial output so that we can log the output of the real-time clock, and if we're plugged into a computer, we can see what the time is. We're defining the action of all of the pins, whether they're output or input, and then we're checking the real-time clock module to see if it exists or if there's a value already stored in it. And if there's not a value, we're going into our startup animation. If there is a value, we're updating the clock and we're writing it out to the display and then jumping into our main loop. The main loop is what runs over and over and over again. Essentially, as long as the Arduino is powered, the main loop is running. We're doing some things at the top, like checking our potentiometer to adjust the brightness. We're handling our minute and hours buttons to see if they've been pressed. If the minute button has been pressed, we increment the minutes. If the hour button has been pressed, we increment the hours. And we handle the rollover. So if minutes go from 59, it doesn't go to 60, it rolls back over to 0. And if hours go from 23, it doesn't go to 24, it rolls back over to 0. And then we check the real-time clock for the time and push that value out to the display with this function called writeClock. That loop just runs continuously about 83 times every second. It takes roughly 12 milliseconds to go through this loop. So every second this loop is happening 83 times, give or take. Then we get into some of our helper functions. Startup sweep is the function that just causes the clock display to sweep up and down if there's no value set in the real-time clock. Then we have this little function, pack BCD, that takes our number, breaks the tens place out, and stores that into the upper half of a byte, and takes the ones place and stores it into the lower half of the byte, the upper nibble and the lower nibble. Then we have writeClock, which actually pushes all of the bit data out to the shift registers and causes the LEDs to update. We effectively turn the display off, we write out hours, minutes, and seconds, and then we turn the display back on, and it happens like that. Then we have update brightness, which reads the value of the potentiometer and maps it from 0, which is LEDs are completely off, to 255, which is LEDs are full brightness, and it puts that value out through pulse width modulation to control the output enable on the shift registers, and that's what gives us our dimming on the LEDs. We have raw write, which is just a bit pattern that goes into the startup animation to give us that nice sweep. It defines the pattern across the LEDs. And then we have print time, which just writes to the serial monitor the current time and the amount of time spent in the main loop so we can see how much work the processor is doing. And if we pull our serial monitor up, we can see that every time print time is called, it outputs the current time and the amount of work in milliseconds, or the amount of time in milliseconds that the CPU spent doing that work. It's not really true CPU load, but it gives us an idea if the CPU is being consistent, which in our case it is. It's always around 1200, 1250 microseconds. So that's our code that runs on the microprocessor. There's not a lot to it, and it's pretty heavily commented. So even if you're not super comfortable working in C code, you can copy this into your Arduino IDE, you can hit compile, you can upload it to your Arduino, and it should just work. We're going to get into a little bit of a time lapse doing some soldering. We're getting the Arduino installed, we're putting sockets in for our shift registers, we're getting all of our resistors installed, and because I didn't use the right-sized resistor footprint in my PCB, I'm having to install those vertically. Not a huge deal, but it was a little bit of an oversight on my part. I'll know to use the right footprint next time. After we get the resistors soldered, I'm going to add the capacitor and the potentiometer, and then I'm installing the real-time clock module. I did find on my circuit board that I had a mistake and I was taking my buttons to VCC instead of to ground. I could fix that in software, but I was getting too much noise in the circuit, so I ended up having to break the trace, bodge a wire in to connect the buttons to ground. It's not pretty, but it works, and if I ever redo these circuit boards and make more, I know that's something that I need to fix. Then I'll start getting my LEDs soldered. And the third mistake that I made is I didn't give myself a landing pad for the negative leg of the LED to connect to the resistor. So unfortunately, we actually have to solder the negative lead of the LED directly to the resistor. Fortunately, we can make it work. Unfortunately, it's not very pretty. So I think that wraps up all of the soldering. It's kind of boring to show soldering in real time, so I just wanted to speed through it. All right, on to more good stuff. And here you can see a little bit more clearly what I'm talking about. I had to bodge this in, so I had to cut this trace and then solder this over here to ground. And then all of these resistors, which are standing upright because they don't fit the pad, are soldered to the negative lead. So that's just soldered here, and then the positive comes down and solders to that pad. Again, it's not the end of the world. It probably doesn't look like a professional made this, but a professional didn't make this. The good news is this works, and it is a clock. Technically a binary clock, but that's still a clock. And minus the buttons, which can't be soldered on until we do final assembly, this is our completed circuit on the custom PCB with all of our timekeeping LEDs attached. It still looks a little suspicious, but a lot less than this looks. So this is what's going to go into our final clock assembly. I've already tested all the LEDs, and I know it's working. I just need to get the final touches done, get the base mounted, solder the buttons on, and put the LEDs in the LED holders. We need to solder our switches on, and this is the one drawback to this setup. Because the switches thread through here and screw on, and they only go out the front, when I solder them on here, they're going to be effectively captive. It's just a shortcoming with this design and these switches. So we need to connect our minutes, which is this switch, and our hours, which is this switch. This is my minutes leads. My hours leads are over here. We're going to solder this all together, and then we'll start routing these LEDs. So this is going to be just a little tricky. And I also have this bodged in wire to contend with. But since the switches share ground, I can solder both of my negatives together into this and then just connect the appropriate other end of the switch where it needs to go. And I do have to get close and take my glasses off because I have old eyes. Should have probably brought my helping hands with me. Didn't have that much foresight today. I also left my wire strippers in the office, which makes this a good bit harder. All right, so minutes goes to, well, let me double check. Because the last thing we want to do is connect this wrong and have to fix it. And I'm glad I double checked because minutes is actually switch 2, hours is switch 1. I would have been really mad at myself if I would have had to have unsoldered that to fix it. All right, now we get to route some LEDs. I was smart enough to set it up so that the first LED in the ones place is here, and the first LED in the tens place is here, all the way across. So in theory, it should be an easy matter of routing from the first ones place to the bottom slot here, and from the first tens place to the bottom slot here, and then just working our way up. So we will get all of these connected now. Let us start routing LEDs. If I was gonna do this over again, I would rethink my cable management. I could actually see daughter boards that go here that hold the LEDs and then just connect with ribbons. We're gonna have to get a little creative here. Just fishing everything together is a little bit of a challenge. Okay, there are our seconds done, and now we move on to our minutes. And I'm realizing as I assemble this that I really put the LEDs in a little backwards. I should have rotated them so that the tens place were on the right, on the left, and the ones place was on the right so that it lined up properly when I got it all situated. I did not make this easy on myself. It is more than a little tangled. There we go. All right, all of our LEDs are in. I think we are ready to fire it up for the first time. If all goes well, we should see an animation sweeping from the bottom to the top and back down. That means we didn't break anything. We got all of the LEDs in the right place and the circuit is functional. So moment of truth here. Hey, look at that. Right LEDs, right place, right order, sweeping up and down. So this is exactly what we want to see. Awesome, good stuff. We are in what is called the startup sweep animation. The reason it's showing this is because there is no time stored in the real-time clock. I don't have a battery in it because I wanted to make sure it goes into this mode. It also helps me figure out if I've got all of the LEDs in the right place because they sweep up and down. So if I had some in a different order or in the wrong place, the pattern would not look like this. So if we push the minutes button, we should now be in time setting mode. And we can see our seconds going, we can see our minutes, and we can see our hours. Everything seems to be working. If we push the hours button, we kill the circuit. Oh, my power bank. That power bank likes to turn off. As I was saying, if we push the hours button, we're in time setting mode and hours should be advancing. And if we push the minutes button, minutes should be advancing. That's awesome. It's doing exactly what we want it to do. We can set the time, which is 9:38 or 2100 hours. So in the evening, we could get the time set. The problem is when this little power bank dies on me again, or rather turns off, it's gonna go back to that startup animation because there is no time set in our real-time clock. What we need to do is get a little CR2032 battery and put it in there. And then when we lose power, it'll just go back to the time that we've set. So let's do that. Okay, I've got a battery in the real-time clock module. We're back to our startup animation. So if I set the time and we just put a random value in, it doesn't really matter for right this minute. We've got the time set. If I disconnect my power supply, obviously it shuts off. In theory, if I plug my power supply back in, we go back to the time we were in because the real-time clock is now battery backed up. So as long as that CR2032 battery powers the real-time clock, our time will always come back. So we're gonna go ahead and get the time set. As I record this, it is 21:41. So let's get our minutes. So there's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 30, 40. It is now 9:42, and we are, 21:42. This is a 24-hour clock. My little battery bank died or turned off. So now we need it to be 2100 hours. So now it is 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21. So the time is now 9:42 p.m. or 21:42 hours. I just wanted to show the potentiometer brightening and dimming the LEDs. So this is full brightness, which is not obnoxiously bright. Far too many LED projects can get ridiculously bright, and I didn't want it to be obnoxious. So this is full brightness, and then as we turn it down, we can dim all the way down, which would be perfect if you were going to put this in a bedroom or other place with people who have light sensitivities in dark places, all the way to completely off. The clock is still running, the circuitry's still powered, there's just nothing that is displaying on the LEDs. So we can turn it back up, and that is the brightness adjustment. Here's a little B-roll of the clock running. I think this came together really well, and I'm really happy with the way this turned out. I think it looks really interesting, and it'll be a unique timepiece and a conversation starter. I have to say this has been a tremendously fulfilling project, mostly because it forced me to stretch myself a little bit as a maker, both from multiple disciplines within woodworking, not that any of them are super advanced, as well as multiple disciplines within electronics, not that any of those were super advanced either. But it forced me out of my comfort zone. It made me think critically about how all of this would need to be built to come together, and it led me to do some things I've never done before, like design my own PCB and get them manufactured. So I'm very happy with this. I think it is a great complement to the original project that I built 10 years ago, and I am really stoked to have this in my collection, being a nerdy way to tell the time. If you want to build any of this yourself, I've got links to all of the files, the schematics, the PCB board files, the Gerbers that you would need if you wanted to make your own PCB boards. I don't have plans for the wood, but that's the great thing about this. You can put these electronics and these guts into whatever case you want. So links for all of that are down below. I would encourage you to go out, push yourself to try and do something that's out of your comfort zone, and try something new. I hope that you really enjoyed this video as much as I enjoyed making it. If you made it this far and you liked what you saw, I would certainly encourage you to give this video a thumbs up and possibly subscribe if you like the things that you've seen on this channel. Thanks so much for watching. Hope you enjoyed it.